Hello everyone. Today the presentation of the topic of our talk will be about once you know how to create a knowledge graph, as Anastasia showed you a few minutes ago, then you want to perform and to compute analytics maybe on top of this knowledge graph. So you want to make something out of it, and this is what we are gonna try to give you a glimpse today. And we are going to present you the SANSA, which is the distributed semantic analytics stack that we have been developing at the University of Bonn. Just before maybe jumping in, if you want also to have it directly on your laptop, or if you want to follow also directly on your laptop, or to play with the notebooks when we will be playing with the notebooks a few minutes later, you can also download it. And somehow kill two birds with one stone and download it directly on your laptop following those few commands. So let's jump in now. First of all, who are we? So we are coming from the Smart Data Analytics Group, which has been founded in 2016 by the Professor Jens Lehmann from the University of Bonn. At the moment, we are a bit more than 40 members. Gravitating orbiting around Jens Lehmann as a professor. There are 10 to 12 postdocs and senior researchers at the moment, and more than 30 PhD students right now. So the core topic of the groups are dealing with the semantic web and artificial intelligence and machine learning in that context. And the group is, I would say, powerful in the academic community, with more than 3,000 citations a year, and we have a strong collaboration with the Fraunhofer EIES from St. Augustine, which is really close to Bonn. So we try also to have all the time some connections with the industry. I am personally Damien Grox from. At the moment, I am working right now at the ADAPT Center from the Trinity College Dublin. I'm a research fellow there, but beforehand I was working in Fraunhofer and also collaborating with the Smart Data Analytics Group. So that's why I'm here today. And my colleague is Hajira Jabin. So Hajira, if you want to say a few words.
Yeah, thank you, Damian. Hello, everyone, and thank you, Valentina, as well, for inviting us here today. So I'm Hajra, and at the moment I'm working as senior data scientist at Center of Excellence of Plant Sciences at University of Cologne, Germany. And before that, I was also working at SDA as a senior researcher and group leader, together with Damian and Professor Lima. And this is my past working history. So today we'll briefly discuss or introduce knowledge graphs, which has already been covered by Anastasia as well. So as we all know that knowledge graphs have been used in research for many decades now, and recently they have gained traction in representing social networks as well. For example, there is a person, he has some Twitter account or Google account, and then there are some other users, they are liking each other's tweets and they're interacting with each other through use of mobile devices or computing devices. And all this information and this interaction can be more intuitively represented as a graph than in tabular format. So another view of knowledge graphs could be taken as social networks as graphs, where there are some people who have friends, and then those friends have more friends, and so on. And we know that there are some people who have more friends than others. And these friendship relationships could be seen like this in form of graphs. And as said earlier, it is more intuitive or more natural to represent these type of relationships as graph rather than as tabular formats or relation database. So another view of knowledge graphs is that, or what knowledge graphs usually do is that they model entities and their relationships, where entities are represented as nodes and edges are relationships. For example, Lily has a friend, and then Lily is interested in Da Vinci and who has painted Mona Lisa, and all these relationships could be represented as graph. An analysis of graphs could be finding the underlying structure of graph or to predict unknown relationships. And examples of graphs are Google Knowledge Graph, Wikipedia, Facebook, and many others. And these are quite large scale, gigabyte, terabyte-sized knowledge graphs. Another view of knowledge graph could be that, for example, there's a company who has customers, and that company is interested in knowing more and more information about their customers. So the information about customers could come from their social media usage or their banking information, their interaction history, their purchase history, their media watching history, their gaming history, and so on and so forth. And this type of knowledge graph-based representation of each customer allows to be more flexible. So you do not need to have all the information for all the customers. And it makes it more flexible and more easier to represent this type of information. So now we'll move on to SANSA, its motivation and vision behind it. Damian will take over from now.
Yes, thank you, Hajra. So actually, as Hajra has just presented, there are lots of initiatives and way to modelize a graph. And especially one of, as it was also mentioned in the previous presentation from Anastasia, there is a standard that has been made available from the W3C, which is RDF. And RDF is a way actually to represent the data and to share then data between applications in an easy way to just formalize the graph as triples. So there are subjects, predicate, and objects, and by making all the statements available about the graph, you can therefore have all the graph available like that. And within the past 2 decades, the number of available structured information through that kind of standards, through RDF, has tremendously increased. And therefore, now at the moment, and already for the past few years, there is a real need for being able to compute operations and to construct and to build applications on top of those knowledge graphs that would be completely scalable. The thing is that from a practical perspective, the developers, the data analysts, they need to spread their knowledge graph across several nodes, because the problem is that the data is so big that you can't hold it directly on top of a single computer. So that's what we meant by scalable. So that's why you have like a distributed environment. And in terms of application, one would need to be able to predict some trends on top of the graph, depending on what it represents. One would like also to be able to compute some link predictions to discover if the graph is not complete in terms of the data it embeds, and also to be able to complete the knowledge base. So those are typically the motivation that have been driving the creation of the SANSA stack. So the distributed context, the large amount of data, and the specific context of, for instance, being able to query and extract information in a geodata context, for instance. More generally, there are also other use cases that we wanted to be able to offer and to compute, such as being able to extract statistics, to quantify the quality of a graph, to check if it hasn't been vandalized or changed. So this is typically a use case on open knowledge graph, because some initiatives are dealing with open data and converting that directly into knowledge graph. And obviously, it's the same case that you can have on Wikipedia. If you want to be sure that the information that are at the moment on the page are true. So there are also ways that we have explored to detect automatically that kind of vandalisms. we wanted also to be able to infer some data, to make some prediction, as I said, but also to be able to cluster also the knowledge graph, to add some, I would say, machine learning flavors on top of everything. And all of that while staying at large scale in a distributed context. So that led us to the vision that Hadjira can present.
Yeah, thank you. So on one hand, we have distributed and scalable systems developed like Apache Hadoop, Apache Spark, Apache Flink. And on the other hand, we have standards to represent data in form of RDF. So we have the semantic technology stack on the right hand, and on the left hand, we have distributed frameworks. So what we have working already for distributed data is distributed file systems like HDFS, Hadoop Distributed File System, and then on top of it, in-memory computing frameworks like Apache Flink or Apache Spark. They offer algorithms, data structures, and programming and APIs to work with distributed computing and distributed data in a scalable manner. So they offer distributed data sets and streams of data sets and many other functionalities. Built using these computing frameworks are also machine learning libraries that work with a very clean and very well-structured data format and offer analytics facilities. However, most of these machine learning libraries require data strictly to be in a predefined format, which has to be very clean and very neat and in a proper format. So on one hand, we have these existing distributed computing frameworks and libraries, and on the other hand, this data that we have, which is growing in size continuously. So the idea behind SANSA is to combine these two, to combine these distributed computing frameworks like Apache Spark and Apache Flink, and to make them work with the data that is already there represented in form of RDF standards. So what SANSA does is it combines these two approaches and it offers several layers or APIs that ingest this RDF data coming in several different formats and to be able to perform query, inference, and analytics. We will cover these details later in this presentation. So now Damian will cover the layer overview of SANSA.
Yeah, thank you. So a few more, like maybe before jumping into the details of the layers, maybe a few more technical details there. As Hadjira was mentioning, the SANSA stack is exclusively at the beginning. Now we have a bit broadened the scope, but it's exclusively working on RDF large-scale data sets to be distributed directly, and it's a processing data flow engine that allows you to build by yourself the bespoke application that you would need. It includes and it's split into several libraries for creating application. So this is what we call the layers, and a bit like the semantic layer cake, you have like various possibilities from reading, querying, inferring, from bottom to top to the machine learning, which is on top, and everything is available actually at the moment on GitHub. And we are trying to release a new version every 6 months, taking into account all the issues that users may have. So in case you'd like to also be part of that big SANSA family, please come. You are welcome. So more into details and layer by layer what we have. So at the very bottom, what is the most important is to be able to deal with data directly. So that's why just on top of the physical layer where effectively you store data, we have like a knowledge distribution and representation layer, which is in charge actually of taking the pieces of RDF data that the user wants to load on the stack, and is in charge of distributing it across the cluster via some Hadoop and HDFS primitives, and then the engine, the SANSA, is able to compute lots of a wide range of features and analytics directly on top of the data before even having the data structures ready for like more complicated analytics. So among those features, obviously you can play with the different representations of RDF, because the RDF might come from different sources. All those data pieces might have some differences in the way they are structured. There are some sub grammar and languages inside of the RDF. So SANSA is able to provide you with a unified, seamless way of tackling all of that. And on top of that, we have some graph processing and partitioning strategies. So the user is also able to decide how the data set will be spread across the cluster. And while loading it, we can, and we'll show you that later, we can also extract some statistics and some quality measures directly on top of the data. And more recently, we have been integrating also some R2RML and RML features. So that has been done by a PhD student who was also working a bit in collaboration with the group of Anastasia. So the idea was also to be able to allow user not to be exclusively working with RDF, but also with some other kind of data sources. So that has been integrated. Considering that once you have the data you want to do something with, one of the layer is also exclusively dealing with how to extract data, which means how to query the data. So to do that, in the semantic web community, there is a language which is named Sparkle, which is a bit, in a way, similar to SQL for the relational world. And then the idea here of that layer is exclusively to take the data that has been already partitioned and split by the RDF layer, and then to take a query, split it into pieces, and then retrieve the relevant pieces of information from each node before outputting the results to the user. So I won't go during that presentation into the various techniques and details and optimizations that we have been developing for SANSA here, because I don't have the time. But the idea, the takeaway message here is that the user can adapt completely the way he or she wants the way the queries are executed. So it's easy to have bespoke solutions at that point and at that stage. I think that now Hajra will give a bit more details on the inference and machine learning layers.
Yes, thank you. So for inference, RDFS and OWL are the standards that contain schema information or rule in addition to assertions or facts in the data. So the main idea of forward chaining inference process is to iteratively apply these inference rules on existing facts that are already present in the knowledge graph to infer new facts. And this process is helpful for deriving new knowledge, for detecting or for detection of inconsistencies. So currently, SANSA supports efficient algorithms for reasoning profiles like RDFS and OWL horse. And this is an overview of how it works, that we take an input ontology, which is converted into RDTs, and based on the existing rules, some filters are applied, and these values are joined or union with each other to find new results that satisfy those resets, and then this new additional information is added to the original knowledge graph. In machine learning, while the majority of machine learning algorithms use feature vectors as input, the machine learning algorithms in SANSA exploit the graph structure and semantics of background knowledge specified using RDF or OWL standards. And this enables the algorithms to exploit the expressivity or semantic information coded inside these graphs, and it helps to attain better performance or even more human understandable results. So what we cover in SANSA are the algorithms like anomaly detection in knowledge graphs, classification of knowledge graphs using terminological decision trees, clustering of these knowledge graphs. We have algorithms like point of interest, DP scan, or k-means to perform clustering. algorithms for link prediction. A relatively new line of research is transforming these RDF data into tensor-based representation, which is more like a three-dimensional matrix, where on one dimension we have entities, on two dimensions we have entities or resources, and third dimension represents the relationships among those resources. And based on these tensor representations, then we have several latent embedding models, and this is also where SANSA is providing some algorithms for knowledge graphs. So in addition, SANSA is also presented as an interactive notebook that you could run in your browser, and this is something that we will demonstrate today in our presentation as well. Here you could visualize the results and you could run the code by skipping the installation natively on your machine and just using it and testing it on your browser.
Yeah, thank you. So this ends the first subsession on computing analytics directly on knowledge graphs. So I don't know, maybe the easiest. I mean, could you, Valentina,
Would you like to share Hajira's screen now?
Yes, please.
Okay.
Thank you very much.
Hajira is the new presenter now.
Okay. Can you see the screen?
Yes, we can. Yes.
Can you see the presentation mode?
Yes.
Yes.
Okay, great. Thank you. So now we come to the hands-on session, that is using SANSA and SANSA notebooks. So for having a single local single node SANSA, you can install SANSA from SANSA Notebooks GitHub repository. This is something that we covered initially as well. And if you need some time, please have a look at this link. And the requirements for this are Docker and Docker Compose. And when you clone this SANSA notebooks, you only need to have run these 5 commands. That is git clone the notebooks. You move into the directory and you execute these 3 commands of make up, and make load data to load the data into HDFS. And then you could go to localhost to look at the SANSA notebooks. So let me show you. So this is the main screen that you would see, and then you can choose between the notebook that you want to run. For example, here I have opened a Spark notebook, and then I have this RDF notebook, and you can choose whichever notebook you want to try from here. Sorry. So before going into details of SANSA itself, we thought that it would be good to cover a very basic word count example, which is also considered as the hello world example in the programming world. So consider the problem of counting the number of occurrences of each word in a large collection of documents. So the possible solution, distributed solution for a classroom could be that you divide this collection of documents among the students in the class, and each person counts the number of words in the given document. And this is done without communication. And then at the end, we can sum the counts from all the documents to give final answer, and this can be done with communication. So following the similar analogy, this is how it works in word count with RDD in Apache Spark. So in this example, what we are doing is we are reading a text file from HDFS, and we've named it text file. So given a file, Spark context reads the file as RDD. And RDD is Resilient Distributed Data Structure, which is a distributed data structure internally, and it internally divides the data into several worker nodes. For example, if we have two worker nodes, so one line of the document goes to one and the other in the other. So each line of the document is considered as one element of the RDD. So in this line, what we are doing, we are applying this map function to all the elements of RDD, and we are converting these values of RDDs into lowercase. So this is how it can be visualized. And then we are applying flat map function, which is splitting these elements of RDD based on the spaces. So therefore, now we have more elements in an RDD than it was before. So map applies a function to all the elements of the RDD, and it does not change the number of elements, whereas flat map can change the number of elements in an RDD. So here we are filtering out the elements which are less than size 2, or keeping the elements which are only greater than size 2. And then we're applying a map function, which is converting this RDD into a pair RDD, where the key is the word itself and value is the number 1. So in this pair RDD, we are applying a function reduce by key, where the key is this element, key is the word itself. So add all the values where the keys are same. So here if you see that bus has only one value, whereas car has one value here and 2 here, so these are summed, and then van has one value here, and these are summed together. So this involves shuffling and communication, but at the end we have counts of all the words that exist in the document. And at the end we are showing the results using word count.take. We are taking only 3 words and showing their sum as a result. And here you can see that this is now an array because everything was brought back to the driver node, and it has converted into a simple array to show the results. So let's see this example in the notebooks. So here it's almost the same code. We are reading a file from HDFS. We are converting it to lowercase, splitting it, filtering it, converting it into a pair RDD, and then taking the tell elements for visualization. And these are the results, as you could see. I hope these are visible. I'm zooming it out a bit. Right, so this is something that you could even write yourself by using these SANSA notebooks. So now we go to SANSA layer by layer, and the first is knowledge distribution and representation layer. This is covered by Tamio.
Yeah, thank you, Hadra. So as I was presenting like a bit sooner in more from a more general, higher perspective, the RDF, the representation layer, the bottommost layer. So let's now have a look at how effectively we can do that directly within the SANSA and the notebooks. So as you know, SANSA, you are able to ingest RDF and OL data using different formats, and this is done through the use of the GINA library, and you have various styles for the interface that you can use. Obviously, as Hydra was explaining a bit later on regarding the machine learning layer, you can have multiple formats to effectively represent the data once it's stored, and it allows obviously some transformation among these formats. So you can also, if you want to use SANSA, even through the notebooks directly to to translate from one format to another. And on top of that, directly in this layer, you can obtain directly some statistics on on the knowledge graph that you are loading. So I think that I have a snippet of code right on that slide to give already you an idea exactly. So to do that, actually, to have some statistics computed, you only need 3 lines of code. So from the developer side, when people really want to extract and to play, if I may say, with the SANSA stack, it's really easy. So first of all, on the first line, you just call the methods, which is like, to explain that the triples, they have that specific format, which is n triples, but you can also have another one. And then from that, you, for instance, find inside the graph a specific node, which is in that case the influence predicate from the ontology. And on top of that, you can directly start computing like statistics, like property usage here, and obtain some nice results within the notebook. So maybe we can go directly in the notebook and have a glimpse on what is available there. So yeah, on the F layer. So typically, yeah, maybe we can go either for the triple reader example. So all those examples, they are already provided directly with the notebook. So if you launch the command of launching the notebooks, you will have out of the box all those examples. So yeah, the example Hajra is highlighting right now is just showing how to, for instance, print or extract directly from the knowledge graph some triples. In that case, we only show that we only out 5 of them, but you can do what you want there. And a bit down, you have like the statistic example. So maybe I don't know if we want to go, yeah, exactly, a bit downer. So the idea here is taking the ldf.nt file. We want to extract the property usage and then display those statistics in a graceful way. And SANSA is through the notebooks is able to directly extract you the nice and to draw nice charts. So we can go maybe directly to the pie. And this is an example of how distributed are the various properties inside your graph. So if you hover, for instance, on the pie, you have the various information that are spread. So the way we have tried to build the SANSA is also to offer directly the user with nice features that helps then people to maybe take decisions or to extract some information. So the dashboard is already providing you with that. And obviously this is only a highlight on few functionalities, but within the notebooks there are many more. I don't know if we want to go deeper in the details on the quality assessment, for instance, or maybe we can come back a bit later in case.
Yeah, I just wanted to show that we have all these algorithms that you can run, like for example, PageRank of resources. So these are all examples that are present in SANSA notebooks, and you can try them. You can change the code as you want and test as you want.
Also change the display. So we have selected the pie chart there, but if you go a bit downer, you can on the fly directly in the platform change them. A bit up. So yeah, you have all the range of various presentation that you can see. So you can have a tabular version, like we click. Yeah, exactly there. Yeah, for instance, you can do what you want immediately there.
Alright, so should I start with the next layer?
We can go on. We can go
on. Should I share the screen with you or?
No. We can continue from there. So we obviously for some time constraints we won't go into the details of each layers, and we thought that the most interesting were the bottom and the topest layer, because it gives you an idea of how to start the process and what you can achieve by the very end. So in terms of machine learning, what we have is that, first of all, we adapt some of the state of the art and some of the main features that are known by the researcher in the machine learning directly on top of that. So we had to align some of the algorithm to make them fitting with the RDF data structure. And in terms of algorithms, we paid attention to provide people with a nice graph clustering algorithms such as the power iteration, the border flow, the link-based, DB-scan, or the modularity-based clustering. And there are also some methods to compute rule mining, to make some outlier detections, and even to work on knowledge graph kernels. I think that the next slide is showing at a glance the scope that we have, but Hajra has already presented that in the previous presentation. And for the rest, let's go a bit deeper into the details of what we have in terms of clustering. So clustering meaning that when you want to group some nodes from the knowledge graph into blocks of the same flavor, and the idea is that depending on the algorithm and the parameters you give to the algorithm, you can change that color of that flavor, that topic that represents each group. So the first one is the power iteration clustering, which works typically on the labels, on the nodes of the graph. So the idea is to group the nodes based on their similarities in terms of topics. So for instance, if you have like a big set of points of interest, using the PIC, you will be able, for instance, to obtain, to group all the restaurants together, all the banks, all the, I don't know, all the swimming pools. So you'll have like a color for each kind of node. And to do that, it's only a few lines of code within the notebook. So we will jump in the notebooks right after to show you that. But in terms of detail, it's really easy. And you can also decide to share and to cluster the nodes using, for instance, a localization, a proximity metric. And this can be done by the DB-scan clustering. So the idea there is to group the nodes if they are close one from another. So obviously, the idea that you would like to have would be to be able to combine, for instance, those kind of clustering methods and approaches. Because if you start to combine them, then let's imagine that you want to combine clustering based on topics and labels, which is the PIC, for instance, and the localization, the proximity clustering, like the DB-scan. If you want to combine, if you could combine the PIC and the DB-scan, then you would be able, for instance, to extract out of the shade directly from the knowledge graph all the points of interest that are sharing both the proximity and the same topic, like all the Italian restaurants in a specific city. And so this is what we have been working on. So the idea that we had, that has been driving us on top of those kind of use cases, was to be able with SANSA to, from the beginning, load some data and be able to extract the relevant pieces with the query layer, to infer some new nodes with the inference, and on top of that, to have a really nice use case which would be able to extract some area of interest in the case of points that would share various metrics together. And I think that we have, exactly. We have, I think, some in the notebooks, some pieces of code, some snippets that could lead to that. So I think we can go in the notebooks directly and select one of the notebooks.
Damian, should I stop sharing and you share?
No,
your screen?
I think we can keep your screen. So open. Oh no, or I can take it. I can take it.
Yes, so I stop sharing and you can share your screen.
Yeah, yeah.
Thank you.
Valentina, could you? Oh yes, perfect. Thank you. Okay, perfect. So I think you can you can see that full screen now. So if I start from the beginning of the platform of the notebooks, among the various notebooks that are provided out of the box, you have one, for instance, based on. So I can show you a bit of the machine learning one. So as you can see from the machine learning one, we are providing the user directly with all the necessary snippets to start playing directly with the clustering examples. So you have here the modularity clustering, here the power iteration clustering, and those are outliers and those are features, but let's focus on those two ones only. And if I want to use them, for instance, in the points of interest example, let's imagine that I have a set of points of interest. I can then start to compute some statistics on top of them. That's what was presenting directly in the RDF layer. But from a point of interest example, then you have this kind of charts presenting how your data set is spread, and then infer knowledge and compute statistics. And if you want, so ranking the points of interest, and if you want, you can even embed some maps there. So the points are not shared at the moment because it would imply to relaunch the full stack, and we don't have completely the time there. But directly with the notebooks, you have that possibilities of having a ready to be used point of interest kind of pipeline ready to go. And if we go on that combination of points of interest that I was mentioning before, you have also a dedicated notebook on piping the clustering directly there. So all the alignment between the clustering methods are already provided there, and you can, if you want, have like a map at the very end, also showing the various clusters that you could have. So I don't think we still have a lot of time to go in the details there. So maybe I'll jump there, the presentation, and finish that. So we have tried within 45 minutes to give you an idea of both the approach and the idea that we have for SANSA, while also showing you the various some of the various notebooks that we have. Obviously, as you can imagine, all those kind of research of efforts, they have been also how to say that, embedded directly into some projects that have been using SANSA. So there are a few projects here that where SANSA is powering parts of the deliverables, the tools that have been developed. And let me mention, for instance, the one on the right hand, which is Slipo. Slipo was mainly focusing on points of interest and predictive analytics on top of that. So that's why within the SANSA also we have used SANSA to compute various pipelines there. That's why also we put a bit the emphasis in the notebooks to provide some visual Slipo related use cases. But SANSA is also powering some parts of the crowd project, which was like streaming big data quality assessments. There are lots of tools on quality assessments also in the SANSA stack. And finally, for those kind of projects, we have been using also SANSA together with a company to directly compute analytics on top of the blockchain. So it's a bit trendy, but the idea was to extract, to to consider the blockchain as a big knowledge graph and then to extract some statistics on top of that. There are also other projects where the SANSA has been involved. It has been also involved in the beta, which is a big data Earth observation technologies, and we were using SANSA there to design some really specific pipelines that were dealing with seismic information. SANSA has also been used in Boost for the European data space, and then more recently, SANSA also has been discussing the Quali Chain project, which is the idea of the Quali Chain is to also provide certifications on diplomas and trainings through the blockchain, so a decentralized chain like so. And then here, SANSA would also play some important roles to help the people from the project to design what they want exactly in the pipelines. Maybe any notes on the conclusion? Maybe Hadra wants to jump there and finalize everything there. Hadra?
Thank you. So as a conclusion, SANSA is a generic open stack for big or large-scale linked data, and it is built on top of state-of-the-art distributed frameworks like Apache Spark and Apache Flink. And it offers out-of-the-box framework for scalable and distributed semantic data analysis, and it combines semantic web and distributed machine learning for RDF representation, querying RDF, inferencing, and analytics of RDF data. We have seen these two layers in more detail than the other two. To the best of our knowledge, it is the first and only stack that offers all of these four functionalities or layers in a single box. And these are the associated publications. And thank you very much from me and Damia.